and quantum phase transitions in Aharonov-Bohm interferometers.
Thank you.
We have 20 minutes.
Yes, sir. Thank you. It is my pleasure, of course, to be here and thank the organizers for the opportunity to tell you about our work. Let me take this down a little bit. This is work done in collaboration with a number of people, as I list here. And I come from Ohio University. So what is it? As this is an audience that is quite diverse, let me just give you a 2-minute introduction to the Kondo effect and try to make connection with what I'm about to tell you in the next few slides. So as some of you I know well, the Kondo effect is this many-body screening of the spin in a spinful quantum dot because of the electrons in the leads. Simple cartoon, a nice introduction was given yesterday by Professor Eto. So here I have a rendition of that idea. Basically, whenever you have an odd number of electrons, like shown in this cartoon, you have an unpaired spin in a simple picture, and so this charge is quantized because of the Coulomb gap. There is an energy gap that is listed here as this EC, being in fact the characteristic energy. And if the temperature is high in some sense, but is still lower than this characteristic energy, the conductance through the dot is blockaded. So you're in the Coulomb blockade regime, and you're at this. Sorry, I keep using not the pointer. You're at this bottom of the conductance curve. Now, on the other hand, if you lower the temperature below a characteristic Kondo temperature, then what happens is that these correlations of coordinated hops, if you will, of the electron in the leads with the electron in the dot become important. And what happens is that this spinful quantum dot becomes a screen. And correspondingly, associated with this screening, there is the appearance of an additional channel on the Fermi energy that at low temperatures then gives rise to an increase in conductance. So in this cartoon, whenever you lower the temperature, this zero conductance level that you saw becomes higher, and electrons, because of this resonance, can traverse the Coulomb blockade region, and the conductance increases. So this is the Kondo effect. There can be a model using an Anderson Hamiltonian, for example, where you consider, in fact, the charge and the spin degrees of freedom of the system. Now, the fact that in these quantum dots you have an amazing degree of freedom to control charge states and in even spin states, if you apply magnetic fields, for example, have given rise to a number of studies, and these are only a few of the experiments. In particular, we are, as in this talk, interested in double quantum dots. Double quantum dots are interesting. I mean, the basic phenomenon I already explained. But if you have a combination of two double dots, you have a number of different effects that can be, depending on parameters, depending on fine-tuning of parameters, accessed experimentally. So these various intradot and interdot parameters, as I list here, include, can be controlled by gate voltages and biases in some cases. And one can access things like physics such as the SU4 Kondo system or RKK interactions if you have spinful dots given distance. Essentially, you can think of these quantum dots as being magnetic impurities with tunable properties, if you will, where you can tune the effective exchange interaction and the effective charging if that is the case. So in addition to giving rise to the explicit Kondo physics, which will exist, strictly speaking, for very large charging energies, you can access a number of other regimes. And so you can, for example, in the upper left corner here, I have an experimental image from the group of Goldhaber-Gordon, where they explore the two-channel Kondo physics in two double dots. So what I'll tell you here today is, in fact, that using these double dot geometries, you can also access an interesting physics of a quantum phase transition. What is this transition? Let me specify a little bit more the model that we're going to use. As I said, these are cartoons for the Anderson model that you can write, in that you have the freedom in this case to think of two dots. This is the simple picture. And they're connected to left and right leads, as shown in the cartoon. And because you can control the levels, you know, these gates that I mentioned before, you can actually tune the upper dot in this case to be the dot that is with a particular charge state. In other words, it will be in the Kondo regime. If it were all by itself at low temperatures, it will exhibit Kondo effect. Now, the lower dot, on the other hand, is tuned in such a way that you're in resonance with one of these states in the dot. In other words, it's not in the Coulomb blockade regime, but it's in fact on a peak of the Coulomb of the conductance trace. So the charge in this dot is not quantized, but is in fact allowed to change freely. What this gives rise to is that even if you have an interaction in this lower dot, the role of this interaction is minor. And for simplicity in what follows, I will consider the case in which that interaction is essentially zero. This happens to be not, it strongly simplifies the presentation, but in fact it doesn't change the results. You can imagine that in this cartoon, you can control also an interdot coupling. You can allow the electrons to hop from dot to dot. And it turns out that, and I won't talk about that here today, but it turns out that you can access also different regimes with that geometry. So here today in particular, I will consider only the parallel geometry, where this lambda factor that I show in that cartoon is zero. This is a technical slide just for the connoisseurs so in the field that these calculations that I'm going to present the results of are done with a numerical renormalization group approach, which it's known to be the most accurate characterization of this kind of physics. All right, and just also a technical point for those of you who are interested. What the cartoon here is trying to indicate, the fact that this blue area is shaded, is that by neglecting the interactions in the lower dot, as I mentioned, I can consider this interacting dot, the upper dot, to be in contact with an effective density of states that is given by the combination, if you will, of not only the left and right leads, but also the lower dot. And this seemingly, simple transformation allows us, first of all, to employ numerical renormalization group in a rather straightforward fashion, but also it allows us to exploit this physics that I'm about to tell you. What happens is that depending on the various parameters that appear in the cartoon, V1, V2, and the lambda, for example, the position of the various levels, you can actually change the shape of the density of the states that the interacting dot sees. So the lower left cartoon shows an example of this delta OV, which is the effective density of a state seen by the electrons in the interacting dot. Why is this important? Now, once I know, once in NRG, I can actually calculate the corresponding local Green's functions accurately, exactly, right, numerically exactly, but no approximations done. Once you have this Green's function, you can calculate all the sort of the conductance of the system, for example. And here I have a characteristic example of the quantities that you can calculate. So this method gives you the flexibility to exploit all the physics with no approximations, and further gives you access to the experimentally accessible quantities. All right. So, as I mentioned, let me focus on the parallel dots, because this is the thing that I want to focus on today. It turns out that for this parallel dot geometry, the effective density of the states that appears happens to have a pseudogap. And a picture of that is shown up here in the upper right corner. You can see this is the delta function, this effective coupling that the interacting dot sees. And I apologize, but the cartoon on the left has actually switched the interacting dot to the bottom rather than the top. And so if you think of the lower, this interacting dot here on the left, it sees, because of the presence of this left and right lead and this additional other dot that is in a Coulomb blockade peak, sees an essentially gapped density of states at the Fermi level for the symmetric case, in the case in which the level in the dot is full is equally far from the Fermi level than the empty level, if you will. Now, in this symmetric case, turns out we're in the pseudogap, and correspondingly, there is no Kondo effect. So here you have a situation where you have all the characteristics, if the interacting dot were connected all by itself to the leads, it will exhibit Kondo effect at a sizable Kondo temperature. Yet, the fact that these electrons can explore this neighborhood and, in fact, tunnel from left to right through this other dot actually suppresses the effective density of states and kills the Kondo effect. You can think of this as an interference, essentially, between the sort of the many-body correlation that appears in the dot, that in the interacting dot, in the single particle light resonance that appears in the non-interacting dot. But bottom line is that it kills the Kondo effect. Now, the appearance of a pseudogap in a system is kind of interesting in other contexts, because, of course, whenever there are strong correlations, say in high-temperature superconductors, for example, in fact, the density of states at the Fermi level is believed to be pseudogap. So have a gap or a density of states that vanishes at a point near the Fermi level. And so, even though there is no long correlations here, all the correlations are local, arising from the dot, you can essentially mimic that physics. Correspondingly, the lower right trace shows the magnetic moment of this interacting dot, that because it sees no density of states to couple to the leads, in fact, remains with a magnetic moment that is not screened by the interaction, like by the characteristic correlations you will see in the Kondo effect. So if I were to trace the magnetic moment as a function of temperature, which is what this trace is doing, you will see that it will remain finite. All right? You're in a local moment phase. However, if I move this dot away from the particle-hole symmetric configuration, namely, I move the level of this interacting level on the left, in my pointer, if it shows this one, if I move it around, I actually go away from particle-hole symmetry. The pseudogap that it used to appear at the Fermi level now has shifted away from the Fermi level, and now I have density of states to couple to, and the dot, in the spin in the dot is correspondingly screened. In that case, I have a Kondo effect, and the magnetic moment, as is shown in the red trace, in fact goes to 0, because it is perfectly screened at low temperatures as it becomes this effective singlet. So the fact that there is this transition gives you, as a function of position of this level, tells you that, in fact, there would be a magical value of this energy level where I can go from a Kondo state, fully screened, long correlations, to a local moment with no correlations. So all of this happens, in principle, at 0 temperature, and therefore I have a quantum phase transition, a boundary phase transition, if you're interested in the technicality. But in all of this happens with 2 quantum dots in variable gates. So I can examine what happens to the characteristic response function. So I know that the magnetic moment is going to be screened at some values, not screened absolutely at others, and that there will be a critical point at which the magnetic moment remains in between, as shown there by the black dots on the right slide here, on the right figure. And so if I want to, for example, understand what will be the signature of this phenomenon in the conductance, then I will need to look at what is the low energy excitations. So I told you that the appearance of a Kondo effect is accompanied by the appearance of a resonance at the Fermi level. And so now, in this system, this resonance appears not at the Fermi level. It appears a little shifted, but I can track it down. And it turns out, and it's very important, that this peak, that depending on the characteristic value of this energy level, appears at a different energy, which makes the effect, in fact, stronger at finite temperatures. So one typical problem of quantum phase transitions that are predicted in you know, pretty much any system is that they require, you know, whenever you go to a finite temperature, the quantum phase transition signatures get softened or erased because, of course, you're going away from the critical point. In this particular case, you're also going away from the critical point, yet the signatures become stronger. There's a bit of a technicality why that is, but it in fact turns out to be the case. So the question is, all right, if I'm interested in looking at this quantum phase transition, how would I do it? Well, there is a procedure that I'll be happy to describe in more detail that we're happy to describe for you in the papers. But you can imagine tuning the various parameters in order to find a maximum in the conductance that will give you the sort of the particle hole neutrality point. And correspondingly, you can monitor the Kondo temperature and the conductance in this signature. And you can see that the signatures that appear in the conductance on the left here are indications, of course, as a function of temperature of what is the characteristic Kondo temperature of the system, which you can tune. Now, once you go into this particle hole symmetric situation, you can actually go into the critical point by tuning the other values. And one example is, in fact, the level at this interacting level. And you can see that the conductance, this is a repeat of some of the traces I showed before, the ones on the left upper corner. My mouse refuses to appear. There you go. You know, the various signatures that I indicated in 2 slides ago are actually shown in the conductance. This is a trace of conductance as a function of the delta E1, which is the level in this interacting dot. And you can see that there are these wings that, in fact, become stronger as the temperature increases. So I mentioned the signature of this quantum phase transition appears stronger at higher temperatures. Now, since this is the Aharonov-Bohm 50th conference, so the one obvious question is, I have a multiply connected path, the magnetic flux can be turned on, and what is the effect? Well, first of all, and I've written an equation there how it does, this effective pseudogap that I showed you before, here clearly amplified at low energies, is in fact lifted as you increase the magnetic flux, because of course, you know, if one can understand this vanishing of the density of the states as an interference phenomenon, the application of a magnetic flux changes phases. Correspondingly, it lifts the pseudogap. And so correspondingly, if you were to look at the spectral function on the left-hand side of the screen, or the corresponding temperatures for the various regimes, you can see that, in fact, the Kondo is restored as the magnetic flux increases. So here I am again having a quantum phase transition from a pseudogap to a Kondo, a pseudogap regime to a non-pseudogap regime, namely a non-Kondo to a Kondo regime, as a function of magnetic flux. And so this will be an example in which, of course, many-body correlations are strongly affected by the phases. And they're accompanied, of course, by a strong dependence on the Kondo temperature on flux. So in summary, this is just a short overview of some of the work we have done, where you can see that playing around with combinations, relatively simple combinations of quantum dots, in this case 2, in a parallel combination gives rise to this interesting physics. So the sort of the commercial, if you want to say it, is that, in fact, you can access interesting quantum phase transitions with a relatively easily, my experimental friends may not like that word, but easily accessible physical system. And all happens, by the way, in the same system. You know, many times the quantum phase transitions happen as a function of doping, say in high TC, and you need to actually change samples. Here, it's all the same sample. You need to tune parameters. So for those of you interested in details, there is a reference that you just published recently. In the 0 minutes I have, let me just, one commercial. My colleague, Nancy Sandler, could not come, and she was supposed to give a talk yesterday. So since she doesn't, let me just say that, in fact, she wanted to talk about the suppression of the Kondo screening by spin-orbit interactions in the presence of Aharonov-Bohm if anybody's interested, there is a reference there as well. Thank you very much. Yes, yes.
To the microphone as well. So, are there questions? Well, I have one.
Oh, yeah.
So there's a question.
There's one over there.
Why is it really a sharp transition? I'm not sure I got it.
Why is it sharp? Because it turns out that you can map this to the one reason. If you go to the original Witov-Fratkin, say, work, where they look at the Kondo Hamiltonian in a pseudogap, they show that in fact there is a critical value of J in that case above which there is Kondo, and that's a sharp transition. And I think, a more intuitive way would be that in fact what you're doing is in fact sampling the density of states around the Fermi level, and you need to gain enough from the screening, you need a large enough J for the screening to have an onset. Now the Kondo temperature is exponentially, right? It has an exponential dependence. So there is a sudden onset in the appearance of the Kondo, except that the Kondo temperature is exponentially small. So okay.
Another question? Well, I would have a question.
Please.
You have shown this Kondo temperature as a function of some parameter, and my question
The phase,
here.
That one. Uh-huh.
So how is the Kondo temperature extracted here? Because it's not uniquely defined.
Correct. Yeah. The signature here is obtained from the magnetic moment trace, a la Wilson.
Okay.
But in fact, you can obtain it, for example, also from the width of the single particle of the quasi-particle picture resonance, and they're always the same within a factor. Since the Kondo temperature is a crossover thing.
Okay, so it would be a possibility to measure. Would be to measure this density of states here.
Correct. Oh, absolutely. We believe the sort of that all of this is measurable. Absolutely. Right.
Okay, I see no more questions, and
Thank you.
let's thank the speaker again.
Thanks.